Okay, so in the following video and the videos that follow it, we're going to be talking about two things: the Rolle's theorem and the mean value theorem. You should definitely take time and read through the notes as I describe what these two results are. The mean value theorem is a very useful result for us, So really, again, encourage you to look at those things. They're both existence theorems. Describe the guarantee something exists, but they don't actually find it, although in these problems we will be also locating the values through algebra. So this problem instructs us to determine if Rolle's theorem applies, and if it does, find all the values that it guarantees, which says, Rolle's theorem says that if these conditions apply, then we can be sure there's some place in the interval where the derivative is 0. So we're going to begin by looking at the function x to the 2/3 on the interval -8 to 8. There are three conditions for Rolle's theorem. First of all, the two endpoints need to have the same function value. Or in the theorem it states f of a equals f of b. So we need to evaluate f of -8. So we go ahead and we plug in -8 into our function. That would give us -8 to the 2/3. Now remember, 2/3, the third, that's a cube root. The fractional part, that's a cube root. So that's cube root of -8. Then raise that to the second power. Or you could take -8, raise it to the second power, and then do the cube root. It actually works either way. So here I'm going to go ahead and do the cube root of -8 first. That leaves me with -2 to the second power, and -2 to the second power is 4. So f of -8 is 4. So for Rolle's theorem to apply, f of 8 has to also be 4. So we go ahead and compute f of 8. F of 8 would be 8 to the 2/3, and again using the same reasoning, being raised to the 2/3 means we need to do the cube root of 8, which is 2, and 2 to the second is 4. So condition 1 is met. The second condition that has to exist for our function is it has to be continuous across that interval. Well, what we really have here, x to the 2/3, that's really the cube root of x squared. Cube roots don't have any issue with domain, and squaring stuff doesn't have any issue with domain. So this thing's defined everywhere, and so therefore it is in fact continuous on that interval. And then we turn to our last condition, which is our function needs to also be differentiable across the whole interval. So we ask the question, is it differentiable? Well, to answer that question, we need to know its derivative, and is the derivative defined across that interval? Well, f prime of x, if you do the derivative of x to the 2/3, would be 2/3 multiplied by the exponent, drop it by 1, x to the -1/3, which we could rewrite the -1/3 by moving the x to the bottom. And we could write that as x to the 1/3 there, or as I did here, cube root of x. So we get 2 over 3, and then we move the x to the bottom, and that x to the 1/3 is cube root of x. Okay. So that's our derivative. Now, is that derivative defined across that whole interval? Well, you might notice there's a 0 in the bottom, or a variable in the bottom, and x equals 0 would make the bottom undefined, and 0 is in that interval. So because it's undefined at x equals 0, and x equals 0 is a point in the interval, then we know that it's not differentiable. And so therefore, we can't guarantee that there's any place where the derivative is 0 in this interval. Okay. It may turn out that there is a place. It actually doesn't in this problem, but that it still could, but we have no guarantee of it happening. Rolle's theorem just guarantees it if those three conditions are met. F of a equals f of b, continuous and differentiable. So since it's not differentiable, we're actually done the problem. Rolle's theorem does not apply. Rolle's theorem does not apply in this particular problem. Okay. If it had, we would go on and actually set about the second part of the problem, which would be solving when is f prime equal to 0 in that interval, which in this case doesn't happen, but you'll see that in the next example.